Hi, my name is Evan Olson, and I'll be solving problem 1.50 from the Fundamentals of Heat and Mass Transfer 8th edition. The problem statement says that there is a spherical stainless steel canister which is used to store reactant chemicals that provide for a uniform heat flux to its inner surface. The canister is suddenly submerged in a liquid bath of temperature of T infinity, which is less than Ti, which is the initial temperature of the canister wall. The first part asks us to develop an equation that governs the variation of the wall temperature with time during the transient process, assuming that there's negligible temperature gradients in the wall. And given an initial rate of change of the wall temperature, finding an initial rate of change of the wall temperature if we're given a interior heat flux. So, since there's negligible thermal gradients, we can just simply do an energy balance between the energy stored, energy in, energy out, and the energy generated. Since we know that there's no energy generation within the wall, we can cancel that term out, and then we can plug in our known values for the rest of the variables. For the stored energy, we have the mass times the specific heat times the change in temperature with respect to time is equal to our energy in term, which is our internal heat flux on this inner surface, times our surface area, and subtracting our convection coefficient times our exterior area times our delta T between the surface and the outer temperature. Since we know that the mass is equivalent to rho times their density times volume, we can plug that in for m, and then we can rearrange the equation for dt, the change in temperature with respect to time of the surface to get this equation here. Since we know it's a spherical geometry, we can use these equations for spherical volume and surface area, plug those into the equation with the values given by the problem, and then solving it, we get a change in temperature of minus 0.088 Kelvin per second. Part B asks us what the steady state temperature of the wall is. This is a pretty simple problem. You just set the energy in equal to the energy out, because there can't be any stored energy in a steady state problem. And we know that the energy in is equal to the heat flux on the interior surface times the interior area, and the energy out is equal to that same convection condition, which is H, or the convection coefficient times the exterior surface area times your times your delta T of that surface. When you rearrange that for Ts and plug in your known values, you get a steady state temperature of 438.9 degrees Kelvin. Part C says that the convection coefficient depends on the velocity associated with fluid flow over the canister and whether the wall temperature is large enough to induce boiling in the liquid. Compute and plot the steady state temperature as a function of H for the range between 100 and 10,000. And is there a value of H below which operation would be unacceptable? So it asks us to plot this steady state temperature plot for different ranges of H. I achieved that in MATLAB just using H between 100 and 10,000, like I said, and it produces this curve here. I then calculated which region, or at what point the temperature of the surface would exceed a critical temperature. I assumed that the cooling bath consisted of water since it wasn't specified in the problem statement. So for water, the critical temperature is 373 Kelvin because that's when it starts boiling, and 373 Kelvin surface temperature occurs at around a convection coefficient value of 950 watts per meter squared Kelvin. And any value of H below 950 watts per meter squared Kelvin would result in slower cooling, which means higher surface temperatures, and so that would be unacceptable operation.